These are supplemental notes for section 1.2 on piecewise functions. They'll probably be given during class, but just in case you're absent or in case you didn't understand it, you'll have this recording to go back and look over. So piecewise functions is something that's covered in Algebra 1, Algebra 2, but just in case you need a refresher, we're going to get pretty in-depth here. So a piecewise function is defined by two or more functions where each equation corresponds to a different part of the domain. So in my first examples here, I've got two piecewise functions, a and b, and piecewise function a is given by f of x, and we see it listed here, and here are two sections of the domain, and then function b is the domain is broken into three different areas. So when we are substituting values in for the function, we simply need to look and see which part of the domain does our value lie. So for f of 1, I need to look at function f and find out where is 1. Is it less than 2 or is it greater than or equal to 2? So I can quickly see that it's less than 2, so I'm going to choose to substitute it in to the 2x minus 1 section, and then I'm going to evaluate that using the order of operations. So 2 minus 1 is 1. F of 2, well, I can see that 2 is in my greater than or equal to section, so I'm going to have to plug that in and substitute that into that part of the domain, or that part of the function. So 3 times 2 is 6 plus 1 equals 7. For function g, first of all, there's a typo here. This is 1/2 x minus 3 up top. So as I'm substituting g of 3, I can see that that is here. That's between 0 and 4. So I'm going to substitute that in for 2x minus 3. So 2 times 3 minus 3, that's 6 minus 3 equals 3. When I go through and do g of negative 6, so negative 6 is going to be up here in this less than 0 section. So I want to substitute that in. Negative 1/2 times negative 6 minus 3. So do the math, and we get 3 minus 3, and g of negative 6 turns out to be 0. The more challenging part of piecewise comes in when we're being asked to graph those functions. So we want to take our two original functions a and b, and we want to graph those functions on a set of coordinate planes. So we're going to think of each condition or domain as a neighborhood separated by a fence. And we're going to shut each fence either with a locked, a solid section of fencing, or we might have a gate where we can pass through that section. So each equation is going to lie in one section of the neighborhood only. So in function a, which there, I can see my coordinate plane and my function here. So I've got a graph for everything x is less than 2. Here's where I'm gonna, that's my boundary line at x equals 2. So I want to graph this function 2x minus 1 on the left side of there, and then on the right side of there is going to be the graph of 3x plus 1. So since my y-axis is in that first boundary, I can just go to the y-intercept, and then I could do a slope of positive 2. So rise 2 and run 1. And I'll go down 2 and run 1 as well, and then I want to use my straight edge to connect those. And then at my boundary line, I'm going to go right up to it, but I'm not going to be able to touch it because my boundary is less than 2. So rather than touching on that line, I'm going to put an open circle right there. So I can go very, very close to that boundary line but not actually touch it. Then for the second part, where I've got on this side x is greater than or equal to 2, and I want to get the graph of 3x plus 1, I can approach this in a couple of different ways. If I want to use traditional graphing, I can, I'm going to get a different color, and I think about what does the graph of that line look like. Well, the intercept is right here at positive 1, and then it has a slope of positive 3. So I'm kind of doing some shadow graphing on this side because I really, that graph does not exist over on that side. It only starts at the boundary line of x equals 2, and then it continues from there. And notice I put a closed circle right at x equals 2 because its x is greater than or equal to. So the rest of that graph on this side of the fence in this part of the neighborhood, that's what the graph looks like. So I use that shadow graphing technique so that I could use my intercept, but I could also use a table of values. So when x equals 2 and I substitute that into my function, 3 times 2 plus 1 is 7. So that would tell me that I could graph 2, 7 as one of the points. And then when x equals 3, 3 times 3 is 9 plus 1 is 10. So that would give me a couple of points that I could graph on there. So it's really up to you which technique you use, just so long as it's a shadow graph that's not in the domain. So let's take a look at B and practice graphing that. So my 3 neighborhoods are going to be 0, and then between 0 and 4, so I've got another boundary line here at positive 4, x equals positive 4, and then so I've got to the left, I've got between the 2 lines, and then I've got to the right, and I've got 3 different functions. So over here I want to do 1/2 x minus 3, so I can go down to negative 3, and since it's less than 0 I want to put an open circle there. And then the slope of 1/2, I can rise 1 and run 2, but that puts me in my other region. So let me go down 1 and left 2 and just plot a few points. So I don't have a ruler handy here, so I just kind of grab whatever to use a nice straight edge. Then here in the central region, I'm going to be between 0 is less than or equal to x is less than 4. So I know I'm going to end up with a closed circle here and an open circle here. Here I had an open circle. And my function is 2x minus 3. So here I am at negative 3 with a closed circle. So I can go ahead and fill that in. And then my slope is positive 2 over 1. So, and then here on this boundary line I'm going to put an open circle and use my straight edge. And then for the final graph I want to do negative x plus 8 and the greater than 4, so that's going to be a closed circle. So I could either go plus 8 and then do some shadow graphing, or why don't I just go ahead for that last function and I'll just make a quick table or substitute my value. What is the value of that function when x equals 4? Well, I substituted in negative x plus 8. So negative 4 plus 8 equals positive 4. So that tells me at 4, 4, so that's an open circle there, then I'm going to have a closed circle there, Then I'm going to go rise and run -1, so that's going to look like this. And that continues forever. So notice on your note sheets here, you've got a space for the domain and range of the function. So I need to look at what values of x is this function defined, and I can see that it has a corresponding f of x value all the way from -infinity to +infinity. However, in my range, I can see my y values go down to -infinity, but then we have a stop right here at y equals 1, 2, 3. And that's going to be a parenthesis because that's an open circle. And then at y equals 5, no, at y equals 7, I've got a closed circle, so that's going to get a bracket. And then that's a line as well, so it goes up to +infinity. So that's going to be how I would notate that. Then if I take a look at my g function, so for my x's, I go all the way from -infinity. I'm continuous. I have a value at 4. I don't have one here, but it picks straight up, so it is a continuous function, which means it's defined all the way from -infinity to +infinity. And then on my range, if I'm looking at my y's, this goes down forever. So that's -infinity. But then, do I ever have a y value that is greater than 5? No. And that's an open circle, so it gets a parenthesis. So that is a visual technique of finding the domain and the range by looking at a graph. So now we're just going to practice graphing piecewise functions. And at this point, if you think this is easy and you know what you're doing, you should go ahead and pause the video and fill these in on your own. Otherwise, I'm going to go ahead and work and fill them in.